Ladies and gentlemen, this is our final vodcast for the semester in Calculus and Vectors, and it's going to be about the intersection of lines and planes. So 2 goals. Number 1, determine how a line intersects with a plane, and number 2, determine the minimum distance between a line and a plane. So prior to getting into the examples, let's take a look at the possibilities in terms of how lines intersect with planes. And firstly, take note that in scenario 1 that we could have intersection at a point, which means you would have a unique solution. Secondly, you could have infinitely many solutions, and that would occur if you happen to have a situation where the line is coincident with the plane, okay, meaning that it entirely lies on the plane, okay, as you can see here. Last but not least, let's give consideration to this scenario, that if the line is parallel, it would have no solutions. Okay, so the line lies entirely above and or below and parallel to the plane, hence no solutions. Later on, what we're going to do is to take a quick look at how, that is here, to determine the distance between any point P on a plane, or any point P in space with another point that is on the plane. Okay, but more to come on that later. Let's consider our first example. We're going to determine if the line and the plane intersect. So take note that the plane is in a particular form of equation. So this here is the standard or scalar form of the equation. Okay, and the line, of course, is given in its vector form. So to begin, there's more than one way to address this, but we'll look at this in terms of 2 strategies. So let's start with strategy 1. Okay, so strategy 1, what we're going to do is we're going to take the parametric equations. So let's substitute the parametric equations into the scalar equation. Okay, and the process of doing that, that is by doing that, what we can do is to determine how the line interacts and or satisfies the equation for the plane. So let's take a look and see what happens here. So notice that for the 3x term, what we'll need is the parametric equation, that is the x component from the vector equation for the line. So that would be minus 1 plus 6t. Okay, so take a moment to see where I'm drawing that from. Minus 4 times y. So the y in this case is minus 1 plus 2t. And then lastly, plus 2 multiplied by the value of z, which is 5 minus 5t. And that's all equal to a value of 11. So let's distribute and we'll combine our terms to just see exactly what's going to happen. So minus 3 plus 18t plus 4 minus 8t plus 10 minus 10t equals 11. Gathering our terms, let's begin with, well, it doesn't really matter. We can go with the constants. So minus 3 and 4, there's 1 plus 10 is 11. Looking at the t terms, 18 less 8 is 10, and 10 minus 10 gives us 0t. So plus 0t is 11. So isolating the t value, 0t equals 0. Okay? So from this, we should be able to take note of a specific relationship between the line and the plane. So notice that 0t equals 0 has many solutions. Okay, it has an infinite number of solutions. So what this implies, okay, is that the line is parallel to the plane, and moreover, not only is it parallel to the plane, but it is also coincident with the plane. Okay, and what that implies is that there are many points of intersection. So many, that is an infinite number or points of intersection. Okay, there are many solutions. So that's one strategy. And what I'm going to do is I'm going to take a moment to clone this page so that I have the main equations in front of me, and then we'll erase what's there and we'll look at a second strategy. Let's clear the ink from this page. Okay. All right. So we're ready for strategy number 2, or method 2. And what we're going to do with this one is we're going to use direction vectors to determine if the planes are parallel or not. Okay? Because if you can tell if they're parallel right from the beginning, then you know that there's not one unique solution. But then you need to figure out if the line and the plane are what we say distinct or separate from each other, or whether they are coincident and have infinite solutions. So let's make a note on examining the direction vectors. Now, because the plane is given in its, again, scalar form, so we have our scalar equation, we need to use the normal vector for that. And then in terms of the vector equation, we have its direction vector here, which can be used. So for the plane, what we can say is that its normal vector, okay, I'm just going to call it n sub, I guess pi being used as a symbol representing a plane, is going to be equal to 3 minus 4, 2. And you can see that that's coming from the coefficients, okay, of each of the terms in the scalar equation. Now, going back to this discussion here of vectors or direction vectors, we can see that for the line, I'll just denote it as L, then its direction vector, we often used M. So M sub L in this case is 6, 2, minus 5. And you can see that here as the direction vector for the line. So it follows that if the direction vectors happen to be perpendicular, right, then we know that the dot product of these vectors is going to be equal to 0. And what was that going to imply? Well, that implies that the line would be parallel to the plane and would be either distinct or coincident with the plane. So in order for us to determine if it's distinct or coincident, it really would be helpful if we knew if a point from the line was actually on the plane. Hence, we could determine if it is coincident. Okay, so let's go ahead, let's look at the dot product just to make sure that we do have, getting ahead of myself here, let's just scroll down. Let's look at the dot product. So let's see, npi dot ml, and let's write the vector down. So 3 minus 4, 2 dot 6, 2 minus 5. Oops, wrong kind of bracket. Is going to be equal to, it looks like we have 18 minus 8 minus 10, which is 0. That's good. Okay. So therefore, we know the direction vectors are going to be perpendicular to each other, which means that the line must be parallel to the plane. And if that's not clear, take a moment to think about it. If this is our plane, okay, and you happen to have a normal vector, okay, so it's a vector coming out of the plane that's perpendicular to it. If you then consider its relationship to a line, so let's say for instance that the line is here, just for the sake of argument, I'm just not saying that it's on the plane. It could very well be above it and distinct, but notice that the right angle that's formed here. So if we prove that the dot product is 0, then we can then appreciate how the green line is parallel to the plane I've drawn in blue. Okay, so let's keep going here. So the line is parallel to the plane. Okay, so last but not least, we need to determine, okay, if they are coincident or distinct. So to determine if L and are distinct, or coincident for that matter, let's substitute a point from the line into the equation for the plane. Okay, if the point satisfies the equation for the plane, then we know that they're coincident. If it does not, they're distinct, yet still parallel, and having no solutions. So let's take a point, and we do have a point available to us. Okay, look back at the line, and you'll notice what we have here, right? We've got minus 1, and 5. So we could take that and substitute it in. So we're going to substitute the point that is x, I'll use round brackets here, point xyz equals minus 1, 5. So the equation for our plane, again, let's go left side, right side on this, was 3x minus 4y plus 2z. So upon substitution, we would end up with, let's see here, minus 3 plus 4 would give us 1 plus 10. So we have 11, and the right-hand side is also 11. So since the left side is equal to the right side, look at exactly what we can conclude here. Okay, we could say that minus 1, 5 is on the plane. So if the point which is on the line is on the plane and the line is parallel to the plane and the line must be coincident and therefore have multiple, many, infinite number of points of intersection. So thus solutions. So thus the line and the plane are coincident. So we're going to end that video there. Please take a moment to summarize your thoughts, reflect on just what was written and stated, and then we'll come back and we'll go through another video. Planes.